without further ado, it's my great pleasure to introduce our next speaker, which is Gary Klein. Gary is a cognitive psychologist and author of Snapshots of the Mind. It's a very interesting field. I've learned a lot about cognitive psychology and KM, so I just can't wait to hear what it's going to have to say about that intersection between cognitive psychology and KM. So, Gary, take it away.
Thank you very much for inviting me. Thank you very much for arranging for me to give this presentation. I'm honored, and I hope I can provide you with maybe one or two types of ideas and techniques that you can take away. I'm going to be talking about a concept called AIQ, which stands for Artificial Intelligence Quotient, and it's a set of tools for dealing with technology. And there's a range of tools today. I'll be talking about 4 of the tools. I'm representing a team that's been working on this for several years. The leader of our team is Joseph Borders, who is here someplace, I believe. Joseph, are you in attendance? I do not see you. Oh, okay. There you are. Good. So if you have technical questions, he's the person. Robert Hoffman at the Institute of Human Machine Cognition is another major part of our team. Shane Mueller at Michigan Technological University is the final part of our team that's been working on this area about artificial intelligence. So what is AIQ? Well, it's a blend of 2 acronyms. It's a blend of AI, artificial intelligence, and IQ, intelligence quotient. And the concept is to increase your intelligence about AI systems, but not just in general about AI systems, but about any specific system that you or your clients might have to work with so that they can work with that system more effectively and more powerfully. We're helping people get smarter, improve their AI, their IQ about the systems they work with, whether it's machine learning, deep neural nets, whatever the capabilities are. And the AIQ tools are to be tailored to specific systems. As you work with them, you would arrange them around the systems that people are operating so it has more bite. It's not just at a general abstract level. So it's a toolkit for working with artificial intelligence and with machine learning by understanding the boundaries and the constraints of those applications, because there are constraints, there are limitations, and people usually don't tell you the limitations. They say, here's how it works, look at all this amazing magic that it performs, all you have to do is this, and yeah, but what happens here? Where can it go wrong? Where can it mislead you? They don't tell you those sorts of things. That's where an AIQ set of tools can come in handy. So the problem is that AI and machine learning are becoming very influential in the field of knowledge management in a number of ways. They're powering digital transformations, connecting people in different ways, extracting concepts from documents, finding patterns using big data. So we're seeing all kinds of wonderful applications of AI, and we can be legitimately excited about that. But the complexity of these systems makes them very opaque. So the people using them often don't understand how they work and what they're doing and how they're thinking, and don't know where the recommendations come from. And what makes it worse is that the AI and machine learning brittleness especially when you deal with uncertain situations. And ambiguity means that the systems aren't going to be perfect. And that unless you're dealing with very constrained problems, you may run into difficulties. And sometimes the system will learn something bizarre, and you won't know why. Let me give you a couple of examples. There's a famous example with Watson, the IBM system Watson. And this is fairly well known. Some of you will already have heard about it. Watson outperformed the best players at Jeopardy, and that's what made it famous. And IBM said, Watson, the wave of the future. Well, we know a number of years later, Watson has not become the wave of the future. Watson has underperformed expectations. But look what happened at the time when it was playing Jeopardy. One of the questions that they had was, this is an American city, and its major airport is named after a World War II hero, and its secondary airport is named after a World War II battle. What's the city? And the humans were able to suss it out. Does anyone know what the city is? Chicago. What's the major airport? O'Hare, named after a World War II aviator. And the secondary airport is Midway, after a World War II battle. What did Watson say? Watson said, Toronto. That doesn't work. Not only is it wrong, it's categorically wrong. And the developers weren't even sure where Watson came up with it, except that possibly in its learning set as it was being trained, it was learning that the name of the category wasn't always that important, and so it was dismissing the fact that it was an American city. So that's an interesting cautionary point. And if you're going to use Watson, you want to know what those cautionary points are, because you need to take them into account if you're going to know how to use it and when to trust it and what its boundary conditions are. Another Watson example. Let's see, I'm going to need my glasses for this. Alex Trebek read the question. It was the anatomical oddity of U.S. gymnast George Iser, who won a gold medal on the parallel bars in 1904. What was the oddity? Well, Ken Jennings sort of remembered something and said that Iser was missing an arm, and that was wrong. Watson, going rapidly through all the cases in 1984, gymnast Iser said a leg. And it was closer, but it was still wrong. Iser was missing a leg. But Watson didn't know that it was missing a leg that was the oddity. And they asked the developers, why did Watson miss that? And the developer said, it was the word oddity. Watson doesn't understand what's odd. That's a concept that doesn't resonate. It resonates with facts and not with relationships like oddity. Well, it's good to know that because it gives us some insights into the way Watson thinks. And that's what we're trying to do when we work with these systems, is get insights into the thinking process inside an otherwise inscrutable system and machine. So the dilemma here is that for many of us, we're going to be responsible for decisions, and decisions that rely on AI and machine learning. And the systems are almost certainly not going to be infallible. And if we don't understand where the recommendations are coming from, and we can't ask it, that puts us in a dilemma. So what can we do about it? because there's resistance growing to the use of AI systems if people can't understand them. And they are opaque. They're working on deep neural nets. Even the developers don't understand how the deep neural nets are working because they set up their systems, feed them thousands, millions of cases. The systems do all their correlational analysis, and nobody knows how it's happening. So the developers don't understand it, and the users don't understand it. So there is resistance. I encountered this resistance in the early 1990s. I was at a briefing in the Pentagon. This was an early generation of AI. We used simple technique, production rules. So very weak AI technology, and people didn't want to use the technology. Physicians didn't want to use them. Battle commanders didn't want to use them. And a colonel who was an advocate for the technology just got impatient, and he said, they'll just have to learn to trust the system. That struck me as not a productive attitude. That struck me as a dangerous attitude even then, that wasn't going to get us very far. And sometimes we do use technologies that we don't understand. We use airbags. We're not sure how they're wired up, but we're happy to have them. We have military aircraft that can immediately sense enemy missiles and fire counter weapons or chaff to protect themselves, and they do it without asking the pilot, is this a good time to do it or not? The pilot is relying on them to pick an optimal time and is happy to do that. Pressing buttons on an elevator, my friends tell me it's not trivial, that there's a lot of complex computations involved. And we don't understand those computations, we don't worry about it. Except when we're at the Marriott and we're trying to figure out how to get to our floor and what's the logic of the system. So sometimes we do have to worry about it. And also financial investors trying to take advantage of short-term blips that they can handle and use to their benefit. But sometimes we don't trust the technologies. A physician diagnosing a patient is not comfortable using the AI recommendation because the AI isn't capable of seeing what the physician is seeing. It can see the vital signs, but it can't look at the patient. It can't look at the patient's color. It can't watch how the patient squirms in pain. It can't watch the patient walking down the hall the way a physician can. Military commanders crafting their tactics. The systems they're working with can compute force ratios, but can't take into account the morale of the troops and nuances of the terrain and factors like that. So you're seeing resistance to the advancing AI programs, and that led to the need to set up a program to try to create more explainable AI. And that became an issue. And the goal of that program is to help people get appropriate trust, not mindless trust, but appropriate trust about when to rely on the system and when not. And that's where AIQ comes in, if it will. So AIQ is a set of cognitive support tools. These are non-algorithmic. These are simple tools that can be put into practice with AI systems, with other kinds of data analytics systems, other kinds of algorithmic systems, but they're mostly focused on AI. And this came out of a DARPA program. The DARPA program was called XAI, Explainable AI. And DARPA put together 11 teams, leading AI researchers from all around the world, each of them trying to take their AI approach and then graft an explanatory capability on top of it so that people could use their system more effectively. This was a 4-year program. I think the budget was north of $70 million, a very ambitious program for these 11 teams. Then there was a 12th team and a separate task. And the 12th team was just a few psychologists. Shane Mueller, who actually understands AI, Robert Hoffman, who's written extensively about it, and me. And I had a unique role in this whole program because of all the people working on it. I think it was pretty clear, at least to me and probably to most of the others, I knew less about AI than anybody else. I'm not a programmer, and my purpose wasn't to try to be a programmer or an AI expert. I was representing the users of these systems to try to identify what counts as an explanation, what counts as a trustworthy explanation. And so I collected data and developed some models for that, using my ignorance, which is massive enough to cover so many programs. It's one of my great tools. So as we're doing this program, I realized we can go further. We can develop our own tools to help people deal with these complex AI systems. And our tools don't have to be algorithmic. Our tools can be much more straightforward, easier to apply, and easier to generalize. And we developed about 8 or 9 tools. Today I'm going to talk about 4 of them. I'm going to talk about a self-explaining scorecard, a cognitive tutorial, a collaborative XAI tool, and a discovery platform. The self-explaining scorecard. This is a basic tool, and you see the entirety. We've written about it. If you're interested, we can send you papers. This came from the realization that all the other 11 teams were taking AI systems and grafting AI capabilities on top. So now the user has to navigate through an AI explanatory system in order to understand another AI system that they're operating. And the notion was we have to give users an explanation. And my team said, no, users, they're trying to come up with their own explanation. It's not that you're giving them an explanation, you're helping them engage in self-explanation. That's what users are. They want to see how these systems work. So what kinds of capabilities are you adding that would help users engage in self-explanation rather than feeding the explanation to them? And we came up with an ordinal scale of what AI systems can do to help users engage in self-explanation. What can you do with this scale? You can use it to hold up against an AI system and see where does it fall. How powerful is it in promoting self-explanation? Most of the AI systems we studied were at the bottom case. No, they don't do anything. This is typically what happens when you field AI systems. A step up would be a feature. It might be a heat map, which is, if you have a visual system, which pixels are the most activated. That's sort of like where the system is paying attention. And that gives you a clue about what the system is thinking about, where it's focusing its energy. A more powerful self-explanatory capability is successes. Tell people about success examples where the system made predictions and recommendations, and people can learn from that. So that's better than just showing the features. More powerful than that is showing the decision logic. Here's the choices that the AI system is making, and here's some of the factors that it's using and how it's weighting these factors. That gives you an even deeper idea about how the system is thinking. More powerful than that is telling about failures. Here's cases where the AI system got it wrong, where Watson said Toronto when asked a question about American cities, or said a leg rather than a missing leg when asked about a gymnast. Of course, this gives you clues, ways to think about how the system might be brittle in some fashion. A more powerful, self-explanatory capability is providing comparisons, showing different conditions so that people can compare one, examine and contrast one to the other, and form their own impression about what each has to offer. And then finally, the most powerful intervention we see to support self-explanation is diagnosing the failures. Why did things go wrong? And maybe even let users break the system, let them play with the system, let them manipulate the system to see how much they can vary before the system starts to fall apart. So these are not algorithmic approaches. These are approaches to help people fully understand, not fully, but more effectively understand how the systems are working. The second tool I want to talk about is something called a cognitive tutorial. And here you're providing users with a tutorial up front to let them know how the system works and how it doesn't work, to explain decisions and how a system might be able to fail, and examples of where it doesn't work, and examples of where users can do a workaround. And a lot of this approach comes from the work that Joseph Borders and I did on mental models. Joseph and I did a project with the petrochemical industry to study the mental models used by panel operators in a high fidelity simulation, as the panel operators had to cope with various malfunctions that we introduced. And we wanted to use that to see what their malfunctions would look like. And I know I went into this believing that a mental model was simply a model of how a system works, right? That makes sense. Your mental model of a system is understanding the parts and the relationships so you know how it works. That was my going in position. And then Joseph and I collected data on 8 different panel operators, and we found that was too shallow. That for the skilled operators, it wasn't that they just knew how the system worked. They also had a good sense of where its boundary conditions are or where it might fail. So that's the upper right-hand corner, how the system can fall apart. And in addition to that, they also had a good idea about what they could do about it, what kind of workarounds they had available if they ran into any of the problems. And that was a powerful part of their mental model, is a set of workarounds and improvisations and adaptations that they had so that they could recover from the failures. And since they were often working with other people, their mental model also included ways that their teammates might get confused, so that they didn't automatically believe what the people out in the plant were telling them. They knew that there are ways that they might get it wrong. So we call this a mental model matrix, and this is a much broader picture of people's mental models than just the upper left-hand corner, where it's how the system works. So let me give you an example. So one of the malfunctions, we were working with a distillation tower. For some strange reason, Joseph decided that we should visit this plant in January or February. The plant is in Alberta, Canada, and it's like minus 11 degrees Fahrenheit, windy, miserable. But Joseph said, this is a good time to visit. And I said, really? So off we go. And we're visiting this plant. And it gets worse than that. So we're visiting the plant, and when we show up, they say, do you want a tour of the plant? And how do you say no when somebody's getting ready to do a project? So of course we want a tour of the plant. So off we go, and I'm bundled up because I don't take cold weather very well. and I'm bundled up, and they say, you've got this nice thick hat? Yeah, you got to take it off, because you've got to have a plastic hard hat with no insulation. So now no earmuffs, nothing like that. I've got a plastic hard hat. And these nice warm gloves, forget about those. You need Nomex gloves that will resist flames, that have no insulation. So we get out, and touring the plant means climbing up metal ladders while the wind is whipping and it's freezing. And I'm climbing up, and what went through my mind was, at that time, this was a number of years ago, I'm 70 years old. Where have I gone wrong? But anyway, here's one of the examples that we came up with. So it's a distillation tower, and there's a problem with the heating system. And so the heat isn't getting to the upper levels the way it's supposed to be, and as a result, ethane isn't getting transformed into ethylene, and so the sensor is showing that it's wrong. So what's happening? So most of the operators said, it's a heating problem, it's in the boilers. So they diagnosed the boilers as the issue. And they looked, and the boilers seemed to be working, so they said, it's a valve. The valve is stuck. We have a frozen valve. But a couple of the operators, at least one, said, if we have a frozen valve, and I can't open the valve, and I can't, because it's frozen, let me try to close the valve. And he could. And so he said, it's not a frozen valve, it's something else. It turned out to be a low-level override. He was able to do the diagnosis. But he could do it because of the way he did the workaround. He wasn't just trying to open the valve, he was testing the valve. That's what a skilled operator does who has a rich mental model. And that's what you want to support, and that's what you want to strengthen. Okay. So, how do we provide cognitive tutorials? Here's an example that comes from Shane Mueller. He's working with students on the Tesla full-scale driving system, and it's a very impressive system. Tesla has a very intelligent system that will drive the car for you. You should be there watching it, but here it's driving down the road, and you can see it's staying on the right-hand side. It's doing what it's supposed to. This is a success story. But what happens if you're driving down a road that doesn't have a middle lane? It drives down the middle of the road. Well, that's sort of unexpected. That's something you might want to know about. And as you inspect the Tesla system, you realize what its limitations are, and it's important to tell drivers what these limitations are so they can take that into account. That's what a cognitive tutorial will alert you to, the limitations, the conditions under which the system is not operating the way it's supposed to. In fact, with lines on the middle, Tesla 80% of the time will stay in the right-hand lane. You remove those lines and it falls down to 20%. So we can show you the data, but it's more effective to show you the pictures and give you the emotional reaction that I can't fully trust the system under these conditions. It's not, I can never trust them. It's under these conditions the system is going to become brittle. Another tool, a third tool in the AIQ's toolkit, I've talked about the self-explaining scorecard. I've talked about the cognitive tutorial. A third tool is a collaborative XAI, which is you're working in an AI system, other people are working with it too. You can all communicate with each other. And if you have an arrangement where I get to hear other people's concerns and complaints and suggestions by entering my own, then you have a community that is trying to educate itself based on what they've learned and share these lessons learned. And this is not hard to set up. It's sort of on the lines of Substack. And there's a prototype using a window-based API and a social credit system that's been set up for this as a replacement for people just putting stickies on the cover of their monitor. A fourth a fourth tool for the AIQ approach is the discovery platform. So let me tell you about the discovery platform. This came about because I was wandering around exhibits during one of these DARPA meetings. And one of the vendors had a system for identifying photographs and said, if you ask it, identify the photographs that have broccoli, it can pull up photographs that have broccoli, and you see there's a heat map, the pixels in the middle of the broccoli. The pixels there are all illuminated, so it looks like the system knows broccoli. And so everybody was impressed, and I'm looking at that, and I'm impressed. But I say, there's also some pixels that are activated on the same plate over the hamburger. What's going on there? Because the hamburger is brown, the broccoli is green. The broccoli has a different shape than the hamburger. And the developers kind of looked a little embarrassed, and they said, we could never figure it out. But then last week, one of the people said, I bet it's the texture. I bet the texture of the hamburger and the texture of the broccoli, somehow the system is conflating those. So they're guessing what the system is getting confused about, but they don't know. Because when you're dealing with machine learning and deep neural nets, nobody knows. So it becomes a guessing game, but you can help this guessing game in various ways. So we thought, why don't we help people make better guesses? Why don't we do that? And so we created a discovery platform to let developers and the operators see the strengths and limitations of their system. And this is an agnostic platform, doesn't need to be customized, and lets developers see the strengths and limitations of their system and how it works and how it doesn't work. And you can shuttle back between a statistical view and a representation of instances, and I'll show you that. I'll give you an example. This comes from Shane Mueller. He said, let's set up a discovery platform for letter recognition. You have a handwritten letter, a number rather. Let's see if the system can identify it correctly. So on the left, he had a whole set of cases where it was a number 4 that was written, and the system correctly identified it as a 4. And if you look at those 4s on the left, they look like 4s, right? Not a big issue. But then he said, let's look at, we know statistically that 4s get confused with 9s. So let's get a random sample of 4s that have been identified as 9s and see what they look like. And those are on the right. Those come from the sample that the system got wrong. Discovery platform lets you play games with these systems in order to make discoveries. You can ask it various questions. Let's look at 4s that are correctly classified. Those are on the left. And they look like pretty good 4s. What about the 4s that were misclassified as 9s? Let's get a random sample of those. And those are on the right. Now, for me, one of the intriguing aspects of this display on the right is that it pulls me in to try to see, why is the system mistaking it? What features are confusing it? How is it misclassifying? What's going wrong? And it's kind of hard to look away. It really engages you into a discovery process. And so the discovery platform is aimed at just that, letting the developers and the users perform this kind of an analysis to gain a clearer idea of how the system is making mistakes and where its boundary conditions are. And if you're interested in the discovery platform, there's a YouTube video that you can pull up, and here's a link to the video. And if you want to play around with the discovery platform with a system that has the number identifications, if you go to the second site, you can play around with it and try different numbers and different kinds of errors and see what you have to vary. So I encourage you to play around with that. But if you want to download the discovery platform, at the bottom is a link to downloading the software. And you can go to the link, download the software. What does it cost? We've tried to make this relatively inexpensive. The cost for downloading the software is $0. So it's a free download. And we hope people will try it and play with it, put it into action, and see what it does. We've applied AIQ in a number of ways. Currently, Joseph Borders is leading an effort that we have going on with the Air Force for AI and machine learning for machine translation. We're looking specifically at a domain where dealing with German media articles about hypersonic missiles and see what kinds of translations are produced and where the translations sometimes get squirrely. So that's one application we have going on. With Raytheon, we've worked with them on a visual question answering system to label photographs. What did they discover? They discovered that their system could really do well with photographs of animals, photographs of sports. But then Bill Ferguson, who is heading that group, said, what kind of sports photographs does it get wrong? Like soccer. It was great at soccer, but not perfect. What's it getting wrong? So he called up a random sample of soccer photographs that got wrong, and he realized these are all from indoor soccer. And that gave him a clue about how the system was doing its identification. I've talked about the Tesla full-scale drive project that Shane Mueller is doing. Another collaborative XAI to help drivers is something that we're working on. There's a precursor of AIQ that we use for Bayesian reasoning. And we hope to get into the area of using AIQ for Bayesian statistics. So there's a number of follow-on applications. In summary, AIQ is just a toolkit of non-algorithmic methods to unpack these systems so that when people say, here's our system, isn't it great? You now have something else to give you the boundary conditions and the workarounds and the confusions so that you can operate it with more confidence and with more appropriate trust. I've described 4 prominent methods: the self-explaining scorecard, the cognitive tutorial, collaborative XAI, and the discovery platform. And we think something like this may be essential for people who have to operate complex technologies. Whether it's the AIQ tools I've described, whether you modify the tools for your own use, whether you add your own tools, I just wanted to make you aware of the importance and the opportunity of creating tools for users to help users make a more effective application and have greater success with all of this opaque technology. So good luck. Thank you for your attention.